A very warm welcome to one and all. Today I, Shivangi Gangwar, a student of Civil Engineering 4th year, Faculty of Engineering and Technology, University of Lucknow, is here to present a seminar presentation on the topic Driverless Metro, the Future of Urban Transit. So here are the table of contents that I'm going to cover further in my presentation. Starting with the introduction. What is a driverless metro? A driverless metro is a train system that can operate without a human crew member. Driverless metro uses a variety of technologies to operate safely and efficiently. These use sensors, intelligent doors, track monitoring system, digital signaling, etc. Although they rely on digital signaling, but they require powerful sensors to analyze the hazards around them and processors that enable them to adapt and even make decisions. They are currently in use in various parts of the world, including Dubai, China, India, Paris, etc. So, what are the benefits of driverless metro? Starting with safety. With automation, the risk of accidents due to fatigue, distraction, or other human factors can be minimized. Efficiency. Driverless metro can maintain optimal speed, reducing delays and ensuring trains run on time. They can also operate with minimal headway between trains, allowing more frequent services, thereby easing congestion. Reliability. Automation ensures that trains run at regular intervals with fewer disruptions, creating more reliable and predictable service that improves passenger satisfaction. Cost. With no need for drivers or operating staff on board, labor costs are significantly reduced. Flexibility. Driverless metro can operate 24/7 without the need for shifts or breaks. This makes them ideal for large cities where public transportation is required at all hours of day and night. Easier expansion. Driverless systems are adaptable to future needs, making it easier to extend lines, add new routes, or upgrade existing infrastructure. Energy efficiency. Driverless metro can optimize acceleration and braking to reduce energy consumption. The technology behind driverless metro is CBTC, which is short for Communication-Based Train Control System. CBTC is a railway signaling system that makes use of telecommunication between train and track equipment for traffic management and infrastructure control. CBTC enables us to know the exact position of train more accurately. The main objective of CBTC is to increase capacity by safely reducing the time interval between trains traveling along the line. CBTC enables real-time communication between train and wayside equipment. Unlike traditional fixed block system, in the modern moving block CBTC system, the protected section for each train is not statically defined by the infrastructure. The trains themselves communicate the exact position to the equipment in the track by means of a bidirectional link, that is through radio communication. Some advantages of CBTC are optimized train speed, automated operations, easy maintenance, minimum trackside equipment, 100% safe, easy expansion. Now let us understand the CBTC architecture. Although a CBTC architecture depends on the supplier and its technical approach, but some of the logical components generally found in a typical CBTC structure are onboard ATP system. It continuously controls the train speed according to safety profile and applies brake if necessary. It is in charge of communication with the wayside ATP in order to exchange information needed for safe operation, which includes speed, braking distance, etc. Next is onboard ATO system. It is responsible for automatic control of traction and braking effort. Its main task is to operate train in fully automatic mode while maintaining traffic regulation targets and passenger comfort. It allows selection of different automatic driving strategies to adapt to the runtime or to reduce power consumption. Next is wayside ATP. It is responsible for management of all communications with the train in its area. It calculates LMA, which is limit of movement authority that every train must respect while operating in that area. Its task is critical for operation and safety. Wayside ATO system. It controls destination and regulation targets of each train. It provides the train with the destination and dwell time in station. It may also perform auxiliary and non-safety tasks like alarm communication and management, handling station commands, etc. Communication system. CBTC integrates a digital network radio system by means of antennas for bidirectional communication between track equipments and train. Usually 2.4 GHz band is used, same as that of Wi-Fi. ATS, Automatic Train Supervision System. It is commonly integrated within most CBTC solutions. Main task of ATS is to act as an interface between the operator and system, thereby managing traffic. Interlocking system. When needed as an independent subsystem, it is in charge of vital control of trackside objectives such as switches, signals, and other related functionality. In simpler networks or lines, it is integrated into wayside ATP. Here is a typical CBTC structure where various components are shown. Grade of automation. Also known as level of automation, it is a standardized framework for categorizing the level of automation in railway operation. It provides clear delineation of roles and responsibilities of human operators and automated system within the train control environment. The grade of automation is classified up to 4 levels. Various grades of automation levels are GOA 0, GOA 1, GOA 2, GOA 3, and finally GOA 4. Starting with GOA 0, manual operation with no automatic train protection. It is entirely reliant on human operations for control and guidance. Driver is responsible for acceleration, braking, adhering to signaling system, etc. GOA 1, manual operation with automatic train protection. ATP monitors train speed, enforces predefined speed limits to enhance safety and prevent accidents. Human driver is in control of critical function. ATP serves as supplementary safety measure. GOA2 semi-automatic train operations. Trains are equipped to perform essential operational tasks autonomously. ATP governs acceleration, deceleration, station stopping, etc. Human operators remain on board through sea operations and intervene in emergencies. GOA3 driverless train operation. Train possesses capability for fully autonomous control under normal conditions. Human operators no longer actively control the train but remain present on board to manage passenger safety, handle emergencies, and intervene when necessary. GOA4 unattended train operation. Fully autonomous train operation with no onboard human operator. Possess advanced sensors, AI algorithms, and communication technologies to navigate tracks and respond to dynamic conditions and ensure safe operation without human intervention. Now let us look into the various case studies of driverless metro, starting with case study 1 of Lille, France. The Lille metro is the first driverless metro in the world. It is two-line rapid transit system. It was started on 25th April in 1983. Its route length is 45 kilometers, covering 60 stations with 2 lines. It is based on VAL technology, which is automatic light vehicle. VAL is a type of automated rubber-tired medium capacity rail transport system. It is based on a concept by a French physicist Robert Gabillard. It was developed at Lille University of Science and Technology and was marketed by Matra and first used for Lille Metro. The VAL technology is now marketed by Siemens. VAL uses fully automated elevated guideways. The maximum speed of Lille Metro is 80 km per hour. The electricity requirement is 750 volt DC. The single ticket price for this metro is £1.8. Here is a map showing the route of the Lille Metro. Now moving on to the case study 2, that is of Dubai, UAE, the Dubai Metro. It has two lines, namely Red Line and Green Line, which were inaugurated in 2009 and 2011 respectively. It is operated by Keolis MHI and it is a two-line rapid transit system covering 49 stations with 9 underground stations. It has a route length of 74.6 kilometers. The technology uses CBTC. Its maximum speed is 95 kilometers per hour. Electricity requirement is 750 volts DC. It uses a third rail which also uses the same electricity. The ticket prices may vary from 3 to 6 AED, that is Arab Emirates Dirham. The following map shows the Dubai Metro route. The red line runs from Center Point to Expo 2020, while the green line runs from Atisalat to Creek. Now moving on to case study 3, which is of Delhi, India. The Delhi Metro Magenta Line. It was started on 25th December 2017. Its route length is 37.46 kilometers, covering 25 stations with 15 stations underground. It is operated by DMRC, Delhi Metro Rail Corporation. The technology uses CBTC. Its maximum speed is 100 km per hour. Electricity requirements is 25 kilovolts. The single ticket price can vary from 10 to 60 INR Indian rupee. The following map shows the Magenta Line route, which runs from Janakpuri West to Botanical Garden. Now let us discuss the drawbacks of driverless metro, starting with high initial cost, which is usually in the form of infrastructure investment and technological upgrades, complex maintenance requirements, Driverless metro requires specialized maintenance and they usually have a higher downtime. Cybersecurity risk. Driverless metros are vulnerable to hacking and there are serious data privacy concerns. Limited human oversight, lack of on-site response, public perception of safety, etc. Limited human interaction, lack of human assistance makes it a bit risky. Integration with existing system. Due to compatibility issues, it cannot be integrated with the existing system. Job losses and system dependency, etc. Now let us look at some of the upcoming projects in the field of driverless metro. Lines 15, 16, 17 and 18 in Paris Metro. Lines 2 and 7 in Mumbai Metro. Thompson East Coastal Line in Singapore MRT. Namma Metro in Bangalore Metro. Lines 1 to 6 in Riyadh Metro. Aqua Line and Purple Line in Pune Metro. Now let us look at a short clip of the Magenta Line driverless metro. Here is a list of references used. That is all. Thank you.